Professor, I'm not sure if I'm alone in this. I'm not able to hear anything you're saying.
Okay, can you hear now?
Yes, sir, I can hear you now.
Okay, sorry, I guess my mic wasn't on. I had thought that I was sharing my audio. So, um, how many people do we have signed in here? Can others raise their hand if they can hear me now? All right, very good. I'm sorry for the um, slow start here. I was trying to get this thing to display who the participants were, and I couldn't get that to come up on the screen. So um, let me, just for the sake of those of you that had not been able to hear, let me just back up a second here, and we'll sort of do a little restart. My name is Larry Steichleather, Dr. Larry Steichleather at NC State University. I have been professor here since 1985. Prior to that, I worked in machinery industry in Milwaukee, Wisconsin. I was with Alice Chalmers Corporation and Bostrom Division of Universal Oil Products. And so what I've listed here for this review, on machine design is a few reference books that might be very helpful to you to have for your exam. The book that I use for the course that I teach is this one, Machine Elements in Mechanical Design by Robert Mort. I'm sure you can find probably any of these readily available online as used books for a fairly reasonable price. And so I started out by defining machine design. What do we mean by machine design? And basically it's a subset of the greater area of problem solving. And it's problem solving related to mechanical systems, which we typically call machines. Machines being an arrangement of bodies or mechanisms, linkages that are usually designed to do work. We want to be able to do work with a machine typically. And so what we're faced with in doing machine design is designing those bodies that are arranged so that we can input power and get power out to do work. And this gives us a um, greater picture here of what we're really talking about. It really comes down, in many cases, to what we would call a whole area of mechanics in the engineering sense of the word, which involves statics and involves dynamics. Statics, of course, as you recall, does not involve time as a factor. And on the other hand, if we're talking about dynamic behavior of machine components, we're involving time, which would possibly involve velocities and accelerations and those types of parameters. And under dynamics, we would have kinematics, and we could also have what's called kinetics. Kinematics would be the study of mechanisms, linkages, four-bar mechanisms, and that sort of thing, which we're only concerned with motion parameters in that case. And whereas we start talking about kinetics, we're talking about forces as well that would be involved in causing the components to move. So the machine design process, or the design process in general, would usually start out with what we call defining the problem. What is it that we're wanting to do? What is the problem? What is the opportunity that we're trying to address? So we need to recognize the need, and we would then define the problem so that we could get an operational definition that would allow us to create a solution or synthesize a solution. At this point, what we would be doing is gathering information. What do we know? What do we not know? What areas of knowledge would be involved in such a problem solution? And then researching those areas, reviewing the physics of the situation, material properties, and so on. And at that point, we would execute the solution, or as I've stated here, prepare a model or prepare a prototype, or in the case of doing engineering calculations, just do the analytical work to arrive at a solution. And so the next step, test, we could call that prototyping, we could call that checking the solution in one way or another to evaluate our our solution. At that point, we may not have a solution that we like, which means that we would be free to loop back and redefine the problem in a slightly different way so that we could arrive at a different solution. So it is a process. It's an iterative process, the whole process of design. And lastly, of course, we have to be able to communicate our solution. That would maybe result in engineering drawings or an engineering report, a recommended design, if you will. What are the details of the solution that we worked out? So, as far as reviewing for a machine design component in a PE exam, I would recommend just reviewing the basics of statics, dynamics, and material properties, strength of materials, if you will. Elasticity, what that means, modulus of elasticity, Hooke's law, material properties, whether they're homogeneous or anisotropic. You have mass and area parameters, which we'll talk about a little bit here in a minute or two. So those would be some of the basic areas that you would want to be familiar with. So here we are. I'm just launching into a little bit of a review here of some of the terminology that you might want to refresh yourself on. And here I'm talking about torque equals I alpha, basic equation that you saw back in physics. That's the rotary motion equivalent of Newton's second law. F equals mass times acceleration. Force equals mass times acceleration. And what we're talking about here in the case of torque being I alpha, I is the mass moment of inertia, which is defined as the integral of the mass times the square of the radius. With respect to an axis of rotation. So if we had, for example, a flywheel or some rotating component, we would be able to calculate the mass moment of inertia, consider its angular acceleration, and be able to determine what torque it would take to accomplish that. So this mass moment of inertia is not to be confused with the area moment of inertia, which is a property of cross sections of beams and the like that we'll talk about here in a few minutes as well. One of the things related to mass moment of inertia is what we call a parallel axis theorem. That is, if we know the mass moment of inertia about, say, an axis through the center of gravity of a component, we can calculate the mass moment of inertia about some other parallel axis simply by adding to the mass moment of inertia about the CG the distance squared times the total mass. And that would give us the moment of inertia about some other axis here, like BB, parallel, this axis being parallel to the original axis through the center of gravity. And this same parallel axis theorem works as well for area moments of inertia if you're dealing with area moment of inertia instead of mass moment of inertia. Let's look at some basic equations related to mass moment of inertia. As I've said, the mass moment of inertia is the mass times the square of the distance of the mass from the axis of rotation, and we sometimes talk about a radius of gyration, k, such that I would be equal to mk squared, where this axis, this radius of gyration would be the distance away from the axis that the entire mass could be all concentrated and still have the same area moment of inertia as the distributed mass has about its axis of rotation. For example, here if we had a solid cylinder, then the formula for mass moment of inertia would be mk squared, which would be m times some radius of gyration squared, but that's equal to 1/2 mr squared, where r is the radius of that cylinder. And that would allow us, of course, to calculate what the radius of gyration would be in that case if we wanted to know that. If the cylinder's hollow, the interesting thing is that the mass moment of inertia is 1/2 m outside diameter squared plus the inside diameter, inside radius squared, outside radius squared plus the inside radius squared. Intuitively, you would think it might be outside minus inside radius squared, but that's not the case, and in fact it would be a good review of basic calculus if you went through the exercise of actually deriving that to show that it is a plus here instead of a minus. So those are just some basic definitions. You can look in any handbook on mechanical design or physics book, and you'll see other formulas for standard shapes of objects, components. Is everybody still on track with us? Raise your hand again if you're hearing me okay and you can see the screen all right. All right, good deal. Thank you. So let's look at a short problem here, just a little exercise. You could take a few minutes, and perhaps you've already looked at these slides and have already tried this. We have a flywheel, round cylindrical mass, saying that it is 20 inches in diameter and it has a mass of 100 kilograms, 100 kilograms mass, and is subject to an input torque of 1,000 Newton meters. Question is, what is the rate of angular acceleration of that body? So I'll just, if you thought about that for a few minutes, let me proceed then in the interest of time here, and we'll look at the solution. We go back to our definition that we had here of torque equals I alpha. Therefore, the angular acceleration is going to be the torque divided by the mass moment of inertia. And we can calculate the mass moment of inertia based on our definition we just had, 1/2 mr squared, which gives us 3.22 kilogram meters square. And that allows us then to calculate the angular acceleration as being 310 radians per second square. On a problem like this, you just have to make sure you're using consistent units. Be clear about the difference between mass and weight. And if we're talking about angular velocities or angular accelerations, we're typically dealing with radians per second or radians per second square in the case of angular acceleration, as we show here. All right. Here's we mentioned the area moment of inertia for cross sections of beams or parts, and that is defined as the area, the integral of the area times the square of the radius from an axis over the entire area. You'd be integrating over the entire area, and if you do that for a rectangular section like this, you'd have that the area moment of inertia about the centroidal axis there would be bh cubed over 12. That's a good formula to remember and have in your portfolio of knowledge. If you're dealing with a triangular shaped object, then we're talking bh cubed over 36. For a circular cross section, pi r to the 4th over 4. Or if we're using diameters, then it would be pi d to the 4th over 64. I mean, if you put d over 2 here for r and take that to the 4th power, you'll come out with pi d to the 4th over 64. And so here I'm just, in this case, showing the for hollow cross section that we would have pi d to the 4th minus inside diameter to the 4th over 64 as the area moment of inertia. So here's another little review problem. We consider a hollow structural tube, and let's say it has dimensions of 8 inches by 12 inches in height. And so, and we'll say the tube thickness is 1/2 an inch on all sides. What is the maximum area moment of inertia in inches to the 4th? So here, of course, we would be applying our formula for a rectangular cross section. So if we look at the solution here, bh cubed over 12 is our equation. And in this case, we have to decide, well, which direction would be the maximum as far as the area moment of inertia is concerned. Well, of course, will Ixx or Iyy be greater? Well, the height is 12. The width or the base is 8. So since we're cubing the height, we would conclude in this case that Ixx would be greater. And so for the hollow tube, we would simply apply the outside dimensions minus the inside dimensions. bh cubed over 12 using the outside dimensions minus bh cubed over 12 using the inside dimensions. So we got 8, 12, we got 7, and 11 because of the 1/2 inch wall thickness. which gives us a net area moment of inertia 375.6. I'm referring here to an older review set of answers which was given there as answer D. Your newer machine review document doesn't have this particular problem in it. So that is sort of a little basic review of some of the things that you'll run into as a designer. But the other thing you'll be faced with as a designer is what we would call perhaps a factor of safety. In other words, they may word a problem saying use a certain factor of safety, or cause you to choose a factor of safety in calculating the allowable load or stress on a part. So what do we mean by factor of safety? Usually the typical nomenclature is capital N for factor safety. It would simply be the allowable load on the material divided by the actual load or actual stress in the material. In other words, if we had a say a yield stress of 60,000 psi, and we were putting a load on it of only what amounted to 30,000 psi, then we'd have a safety factor. We'd be designing with a safety factor of 2 in that case. More generally, we could say that the load which will cause failure divided by the load which is actually existing on the part. Now, one point of discussion here is that a load which will cause failure in a machine is not always a load which would actually cause a part to fracture or actually physically fail. It may fail because of no longer functioning properly. In other words, for example, if you had a shaft with gears on it that were loading the shaft, and if you simply had a shaft that had too much flexure in it for the gears to mesh properly, that would be defined as a failed design or an unsatisfactory design. So the load which causes the part not to function properly divided by the load which actually exists hopefully would give you a factor of safety. We do not want to design right up to the point of failure or up to the load which would cause malfunction or unsatisfactory function in a part. And here I'm simply listing out some examples of the factor safety ranges. If we very well know our materials and we are very certain about loads and we have controlled environments for this part to operate in, when we can get by with a factor of safety which is in the neighborhood of 1 or slightly over 1. But in the case of certainly in the case of agricultural machines, oftentimes we may know the material properties, but we may have some uncertainty about how this thing is going to be used or what the range of loads might be. And also there might be uncertainty associated with the environment in which it's going to be operating. Certainly a great range of temperatures and possibly corrosive environments over time and that sort of thing, which would cause us to use higher factors of safety, maybe up to 3 or 4. But this becomes a matter of policy, corporate policy in most cases, as to what the designers would be expected to use in the design of a machine. Also depends a lot on what's the expected life of the machine, what's the what are the safety hazards or uh, liability hazards involved in case of a failure and that sort of thing. All of these things would go into a policy regarding what factor safety one ought to be using in a case like that. So let's back up here or go to some just really basic considerations of design relationships for what we could call elastic design. Usually we're designing in the elastic range. That is, we usually are not designing parts that go beyond the yield point stress-wise in a piece of material. Some parts get designed over into the plastic range, perhaps though, like ROP structures on tractors. They're designed to absorb energy, and so deformation is allowed and expected in those applications. But for most parts, we're designing well below the yield stress. So in other words, we'd be designing for a maximum stress of yield divided by our safety factor, our factor of safety. So in the case of axial loading, of course, we remember that's just the force divided by the cross-sectional area of the part. That is, be like a column loading or axial loading in a rod or a truss member of that sort. And that's pretty straightforward. In the case of transverse shear, we might have a case like a beam, maybe a cantilever beam, for example, where we're interested in what is the shear stress. And I've simply listed here where V is the vertical shear, which essentially would be the load on the part, for various shapes of parts. You can calculate the maximum shear stress there on that on such a part. And then, of course, we can have bending. Bending is a very common thing that designers, machine designers, would want to be familiar with and will be dealing with. Because whether you're dealing with any kind of a part that has bending moments applied to it, then you're going to have bending in your part. So, for example, here we would remember that the maximum, get my arrow here, the maximum the stress that you would want to design for in bending would be the yield stress divided by your factor of safety. This is considering static loading now. And we say that that is the bending moment times C divided by the area moment of inertia. MC over I, or you might see it expressed as the moment divided by the section modulus. Where C is the distance, we'd have a neutral axis in a beam like this where we've got, say, tensile loads above, we got compressive loads down below the neutral axis. But the distance from the neutral axis to the outer fiber of the beam would be where the maximum bending stress would be occurring. I've got these 2 points A and B here just to show you if you were asked to calculate the bending stress, say at point B or at point A, what you would need to be able to do would be to determine what is the bending moment at that location on the beam. And I think you can appreciate that in a cantilever beam like this, the bending moment is going to be increasing because of increasing distance here. Then it'll be increasing all the way back to the wall here. So the bending moment at point A will be greater than the bending moment at point B, which would enter into your calculation. So let's look at an example or so here. If we're applying, we're talking about axial loading, then we're going to be applying what's called Hooke's law for stresses and strains. And very simply, that is that the stress, in this case, for axial loading, the stress in the x direction, sigma x, is equal to E, which is the modulus of elasticity, times the strain. And we also know that that is the force divided by the area, a cross-sectional area. We also know that the strain is defined as the change in length over the length, or the original length. Change in length over the original length. So if that's equal to P over EA from this equation here, we can then determine the change in length for a given load, PL over EA. That might be a good question to have on an exam. If you apply a certain load to a rod of a certain diameter and a certain length, what would be the change in length of it if it's steel or aluminum? And that, whatever the material, you'd have to then determine the modulus of elasticity, E, for that material. So here we're simply giving you a reminder that the stress is a function of the strain in a part, and the relationship is determined by the modulus of elasticity. So here is a little problem. We have a round rod, 1 inch in diameter, 10 feet long, and of course you might be accustomed to using metric units. You might want to be using metric units in an exam, but it's just a matter of doing the proper conversions. I'm simply have chosen to use the English units here. So in this case, let's say we're applying a tensile load of 10,000 pounds force, and it was determined that the rod increased in length by 140 thousandths of an inch. The question is, what type of material is the bar made of? So basically, as you think through that, you're going to define the problem. The problem is we need to determine what the material is. What do we know about the material? Each type of material would have a different modulus of elasticity, E. So perhaps that would be our key for determining perhaps what kind of material it is. And so let's look at the possible solution here. We review again our basically Hooke's law. This is a generalized Hooke's law statement here, that the strain in the x direction is the stress in the x direction divided by the modulus of elasticity, which we've said. But this includes the possibility of having stresses in two other orthogonal directions here. And in the case of an axial load, though, these are zero. We'd have stress in the x direction, but sigma y, sigma z would be zero. We'd have to know something about Poisson's ratio in this case if we had loads in those other directions, and that's simply the the ratio of the, let's say, the transverse strain to the axial strain for the material. And in the case of most metals, it would be in the neighborhood of 0.3. So let's look at where this takes us then. Tensile load gives us sigma y, sigma z, 0. Sigma x then is our tensile load. We can calculate that stress, 12,700 psi. And then Since we know that the stress is E times the strain, we can calculate, we have enough information here to calculate that modulus of elasticity. That wasn't given to us. We're having to calculate that. That's going to be the key to what kind of material this was. So we do that little calculation. We come out with 10.9 times 10 to the 6 psi as the apparent modulus of elasticity. So if you go look in a handbook for moduli of elasticity for materials, we'll see that that pretty well fits about where aluminum comes out. And so that would be the answer to our, one of the answers to our problem here. Aluminum would be the material based on the information given. Now, here's another question. How did the diameter change for this particular rod? Well, we know that the change in diameter is the strain in the transverse direction times the original diameter. So that would be the Poisson's ratio times the strain in the x direction over E. This gives us Poisson's ratio times the strain in the x direction would give us the strain in the y direction according to Hooke's law. And so that comes out to be negative, that is, it decreased in diameter, 0.00035 inches per inch. Definition of strain, changing length over length gives us inches per inch as units there. And so that would be that answer. So that just is a little type of a little problem that would be nice on an exam of this kind. I'm not saying that's what you'll have. I don't know what you might have, but this is. Let's look at some combined loads here. I want to part. Apologize for the freehand sketching here, but what we have is an axle which is stubbed into a frame of some sort on a machine, and on that axle we have a wheel which has a tire in contact with the ground. We have two bearings that are separated from the either side of the wheel by 2.5 inches and by 3 inches, and the axle is 15 inches above the ground, and we have a side load on the wheel there of 300 pounds force, let's say. And we also have, of course, based on this free body diagram, we have a vertical load that our wheel is carrying of 1,000 pounds. So the question then would be, what is the maximum direct stress developed in our axle at this location, AA? So what we have to do then is, in our planning for the solution, we're going to sum forces and moments. We want to ultimately get to the bending moment, and we want to get to the bending stress, and we want to get to the tensile or compressive stresses in the axle, so that it would be, excuse me, combining, those tensile loads or compressive loads would be combining with the bending stress on a part. So here we're going to sum forces in the x direction, and those are that would come out to be 300 pounds, as we said. That's our side load on the bottom of the wheel there. And then, so some moments about the section AA at the neutral axis of the axle. And that would give us 1,000 pounds times that 3-inch offset wheel. And then we've got that 300-pound side load, and it's offset 15 inches, which would give us a total bending moment there of 15 inch-pound force on the axle cross section. And so then, at that point, we can apply our little equation for bending stress, MC over I, calculate our I here um, for this axle. In this case, our the C, or the distance here from the neutral axis, is going to be the radius of the axle. And this would then allow us to plug in our bending moment, plug in our diameter, or a radius rather, and we calculate then our bending stress. And then in addition to that, we have an axial load in that axle because of that 300-pound side load. And so that amounts to 382 psi. And so as far as the tensile load on the outer fiber of that axle, it would be the bending stress plus that tensile load, which gives us a combined stress there of in the neighborhood of 77,000 psi. All right, moving on here. Let's look at briefly the stress due to torsion. The torsional stress would be the shear stress. That is the yield stress in shear divided by our factor of safety. That is, we would not want to design any higher than the yield in shear divided by our factor of safety. But that stress is going to be the torque times the radius of a circular cylindrical part like this divided by J, where J is the polar, called a polar moment of inertia. That is the polar area moment of inertia, which is simply the sum of Ixx plus Iyy. And so if we look at the equations for that, we'll see that it is pi d to the fourth over 32. Well, basically, it's twice what the area moment of inertia is about an axis through the cross section. And in the case of a hollow torque tube, then it's, of course, we're taking off the difference there due to the void space in the center of the part. So, where does this take us? We're here looking at the combined stresses that we would have in a part. And I don't want to get too much detail here, but you'll recall one thing you might want to review is Moore's circle, which is used for computing the principal stresses, where you have stress in two different directions, and you also have the possibility of shear stress involved. So that allows us to calculate the maximum shear stress, plus or minus the difference between those two over 2 squared, is just taking the average of them, and so on. I don't want to get too deep here. I'll lose us all in the nomenclature, but hopefully you can go back and pull out your machine design reference book and look at Moore's circle, give you a discussion of what's involved in dealing with combined stresses. But all I wanted to show you here is that in this is a whole topic called shaft design, and in that case, we're generally dealing only with bending and torsion, where sigma y is equal to 0. Um, and so in that case, we end up with our principal stresses giving us this equation here, where sigma y was 0. And we end up with a torsional stress, or shear stress rather. And so for that we can calculate the bending stress and the torsional stress, and that would take us into what kind of theory of failure are we wanting to apply for ductile materials. We would generally be using what would be called the uh, maximum shear stress theory of failure. Maximum normal stress would be applied to materials that are strong in shear but weak in tension and compressing. And an example of that would be cast iron, where it is good in shear but it's not good in tension. And, well, it might be good in compression also, but not good in tension. And so here I've just got some criteria for how you would apply that. The criteria yield over your factor safety would be where you'd want to go with your maximum design stress. And for brittle materials, we don't have a yield stress, we have an ultimate stress capability. That is, it would fracture at some point, and we certainly wouldn't want to design up to that point. So we'd be designing for less than the ultimate uh, stress divided by our factor of safety. This is very brief here, but this would also lead us into designing for fatigue loads. If we were dealing with a rotating shaft, for example, that had a sprocket or a V-belt sheave on it, where as it rotates, the shaft is seeing a reciprocating, any fiber on the surface of the shaft would be undergoing compression and tension during each rotation due to the bending stress in the shaft that would result from the load from the chain or the belt or the gear might be. And so we'd have a situation where we've got cyclical stresses occurring. And that takes us into a realm which is somewhat different from designing for static loads. And if we were to take a idealized specimen of material and load it to a certain stress level and then cycle it a certain number of cycles, we'll get failure. We'll get failure after a certain number of cycles if the stress is greater than what we call the endurance limit. For ferrous materials like steel, iron, we would find out, and you can go look in handbooks and you can find a plot of data. These little dots indicate scatter a bunch of specimens that were tested. But it would generally follow a line which continues to require less and less stress for increased numbers of cycles until you get to the endurance limit, and then theoretically you might be able to go several million cycles without failure. It would level off. Uh, Non-ferrous materials, copper, aluminum, and so on, do not exhibit a distinct endurance limit, and they would continue down, and at some point you would get failure even at very low uh, cyclical stress levels. And so what the designer has to do if you're dealing with a range load or a cyclical load on a part like this is to remember that this data called endurance limit for the material is for a polished, small, polished, ideal specimen of the material. In reality, our parts are not made out of polished, defect-free um, uh, parts or materials. They're larger, having greater probability of defects. They have maybe surface imperfections, maybe wells, maybe holes, maybe other features which would cause us to derate that material. And this is you can consider this to be a series of fudge factors for wells, for surface area, reliability. If you wanted it to be 99.99% reliable, then of course that factor is going to be large because you're dealing with going out to the third standard deviation or greater on materials. And so basically, if you had a material, maybe you're working with a steel that had a yield stress of say 60,000 psi. By the time you consider that for fatigue application and apply a number of these factors here to the endurance limit, which you can go into a handbook and find. And you can go into Machine Design Handbook and find typical values of factors like these. You might be down to needing to design to a stress range or stress level of maybe 9 or 10,000 psi, a lot lower than what yield would be if you were dealing with static. So anyway, that's simply an area to have a little bit of understanding of. I don't know what the probability that they'd have you get into a problem like this might be, but just need to understand that in the case of fatigue failures, fatigue design, you're dealing with a little different animal than if you're dealing with static stress ranges that can be used. You might see something related to what's called a Soderberg or there's some other names for these failure lines, but it's not really hard to understand. This would be our endurance limit. All it's saying is that if we have no mean stress, no mean bending stress, for example, in the part, we're only dealing with cyclical loading, then we could design right up here to the endurance limit divided by the factor of safety. But if we have range loading, that is cyclical loading, combined with a mean stress level, then we begin to have to diminish the cyclical stress level as we increase the mean stress level. If we had no cyclical loading, you see it brings us right here to where we were, yield point divided by the factor safety. So that's just you'd want to be designing generally in this region, and a designer would need to look at that. Where are you in this cyclical stress versus mean stress range for the part, and to make sure you're not outside here where you'd be getting failure of the part. Um, and if we're dealing with uh, shaft design, typically what we would be using would be what's called the shear theory of failure, where we're dealing with the shear stress. And we'd then be dealing with the endurance, allowable endurance range uh, in shear. And this 2 here is simply indicating that in shear, for steel, for example, the allowable shear stress is about half of what it would be in tensile. You can also go into a machine design book and you can see a chart that would tell you um, the yield stress in shear as compared to the yield stress in tension for the various materials. And I think for steel it's arranged around 0.58, somewhere in that neighborhood. Um, so for ductile materials, that's what I'm not going to go into much more detail here. I just wanted to show you that there is a little equation that can be applied for sizing a shaft. For example, if you know the bending moment that's being applied by the loads on the shaft as it's rotating, and you know the torsional load that the shaft is carrying, and you know the yield point of the material, and you know your allowable um, working stress, S of E, and then you see what that's doing is multiplying. This is going to be much smaller than the yield. So you're going to, basically, this is multiplying the severity of that bending moment. And then you got a little shock factor in bending. You got a shock factor you could have in torsion, which might be fairly low in case, depending on the application. If it were a reciprocating plunger on a baler or something like that, you might have a 2 or 3 shock factor on torsion that you'd be dealing with. But that's a designer's choice. I think as long as you explain what decisions you're making, you're okay. But basically, we got our safety factor, we got our yield stress for the material. Pi, we can calculate the diameter, the outside diameter required for the shaft. And this would be a TIG type application. Uh, so here I'm simply pointing out that in the case of shaft design, we can be dealing with some criteria other than stress failure. As I said before, failure is not always related to actual fracture of a part or bending of a part or permanent deformation in a part. Uh, Torsional rigidity might be an important factor. That is, if you were trying to keep components on 2 ends of a shaft synchronized precisely, then you'd be worried about torsional rigidity. How much wind-up might you get in a shaft like that? So this is a little formula for calculating the theta wind-up due to a given torque for a length of shaft. And this is your shear modulus of elasticity, G, as defined here. And So moving right along, let you wrestle with that a little more on your own. Here's just another little review problem. Perhaps you've looked at it. Here's just another little example. It would be a nice little problem on a test. We've got says we've got a drive here on a grinding operation. We got a shaft. Obviously, we got two bearings. These would be considered self-aligning bearings, so that they're not going to be cantilevering the shaft. They'll be able to accommodate flexure in the shaft. And then we've got a sprocket for a number 80 roller chain with 40 teeth on it. And it's transmitting 20 horsepower at 1,000 RPM. And so we go to a free body diagram of our shaft here. We've got a support 20 inches over. We got another support, which is our bearing. But this sprocket is overhanging that bearing by 4 inches. And so then we have a load on the shaft that would be caused by the chain transmitting that horsepower. Wow, where does that take us? Well, that means we've got to know a little bit about some of the basic relationships for horsepower and torque and speed. We need to know something about roller chain because we're probably going to need to know the radius of this sprocket, and it's not given to us here. All we're told it is number 80 roller chain with 40 teeth on the sprocket. We're also told that we want to find the diameter of this shaft with being made out of 1018 steel. And if we read the problem carefully, we also note that it's not telling us to design, in fact, it's telling us to ignore fatigue. And it's telling us to design for a safety factor of 2. So perhaps you've looked at this already. Let me just, in the interest of time, look at my solution synthesis here. We have 2 types of load on the shaft. We have a bending load due to that chain force, and we also have a torsion load determined by the power being transmitted. That horsepower is being transmitted to some other sprocket on or sheave on the shaft. So there's obviously a torsion load between the two. So basically what we're saying is, as we define our problem and think about it, we got to compute the torque to get the chain force. And here's another little equation that would be good to have in your hip pocket. And again, in customary U.S. units here, we got horsepower equals torque times, and it's unfortunate use of nomenclature here, but N is also usually used for RPM, but it's torque in inch-pounds force times RPM divided by a constant here, which is 63,025. Many times we just use it as 63,000, forget the 25, but it is a conversion for getting us from inch-pounds times RPM to horsepower. So if we do that, we can calculate the torque. 20 horsepower, what we're dealing with, and we got 1,000 RPM, gives us 1,260 inch-pounds force for the torque at that sprocket. Now then, we must know the pitch radius. Pitch radius is the effective rolling radius of a chain on a sprocket. It's not the outside diameter of the sprocket, but it's a little less than that. It's essentially it's the radius of where the pins in the roller chain are located. We're told we have 40 to sprocket number 80 roller chain, how do we compute the pitch diameter? Well, we have to know something about the designation of roller chain. Roller chain, the number for roller chain is, at least the first digit is the number of 1/8 of an inch pitch. So in a case of an number 80 chain, it would be 8/8 of an inch pitch. That would be link to link distance. And so in this case, it would be 1 inch. The pitch of our chain here would be 1. If we had a number 60 chain, then we'd be dealing with 6/8. So we'd be on a 3/4 inch pitch. And number 30 chain, 3/8 of an inch, and so on. Sometimes that second digit is just to designate whether it's rollerless chain or whether it's light duty chain or what have you, but that's not so important as this getting the pitch right. So circumference, we would go to the circumference. Circumference of the sprocket would be 40 teeth times the 1 inch pitch. Since there's 40 teeth, that would give us 40-inch circumference, which allows us to calculate the pitch diameter as being 12.74 inches, or our radius of 6.37. And so then we can calculate the force on the chain. In the case of a roller chain, the slack side is 0. Consider to be 0. You don't tighten the chain so that you have tension in the slack side. You'd be over tightening the chain in that case. So you're dealing only with the tight side force, which would be the force. The torque would be the force times the radius of the sprocket. Gives us 197.8 pounds force in this case. Just a side note here, if this were a V-belt, if this were a belt or a synchronous belt, you'd have a slack side tension, you'd have a tight side tension. To get the torque, you'd have to be taking the tight side minus the slack side tension times the radius. The difference between the two times the radius would give you the torque. And so, moving on then to our free body diagram, which we can complete a little better now, we've got this tension load. Load on the end of the shaft there, which causes us to need to calculate the reaction loads. We also know that we have a torsional moment in the shaft, which is equal to our torque. And so I come right to our shaft sizing equation, recognizing that we're not dealing with fatigue, so we're going to take our allowable endurance limit to be the yield stress. We're going to design that thing right up to static yield stress. In this case, we're ignoring fatigue. And so that term there becomes 1. And these two factors here, shock and bending, shock and torsion, designer's choice. The author of this problem used factors of 3, which would be a fairly severe shock loads for that application. So if we plug this through, what we're needing to do here, if I can back up one, we still need to know what that yield stress is, and we remember it was 1018 steel. Well, we turn in our handbook, or I've put some appendix pages into this review here. We look and see what has happened not to have 1018 in there. So what are we going to do? Well, we go and we interpolate between the 1020 and 1015. And if we do that, we can come out saying, well, it's about 62,000 psi for the yield. Plug all that in, our factor of safety, our yield stress, our bending moment, our torsion, our factors, shock factors, gives us a diameter of the shaft of 1.14. Well, we don't want to machine a shaft of that odd size, so we go to the next standard shaft size. Say an 1.25 inch shaft would probably be our choice in that case. Now, here's another little review possibility for you. You ought to be able to look at a free body diagram like this of a beam and be able to sketch the shear diagram and the bending moment diagram for that shaft. And so hopefully that's an area you would review a little bit, but let's see where we go with that. In this case, to do that, I had to calculate the reaction loads. Well, way to get reaction loads, we got two loads, and we need two equations so that we can solve for those two unknowns. Well, one equation is just the sum of the forces in the y direction equals 0. R1, or R left and R right, and the minus 197.8 equals 0. And then the other equation we can usually get by the sum of the moments. Sum of the moments about any point on the shaft, but usually it's easier to sum about one of the bearings or the other. So I simply chose to sum the moments about the left bearing, and it gave me this equation. Applying the right-hand rule, we got 20 times that reaction load. That would be the length of the beam or distance between the bearings, minus the 197.8 times 24, which is that lever arm, equals 0, which lets us solve for the right reaction load. And once we've got the right reaction load, we can go up here and solve for the left reaction load. That's just a little review of how to get reaction loads in a beam. And then this is what I would do for the shear and moment diagram. And let me just comment on how I get this. I think if I go to the next figure, I can illustrate this a little better. I like to think of this. Let me see if I can draw a figure here. If I can draw a, well, anyway, assume you're a person standing on this beam right here. You're a person standing on the beam here, and you're looking down at, excuse me, let me get back to my pointer here. If you're standing on this beam and you're looking down at this face here, this is considered positive shear, and if you saw the beam in two, if you saw the shaft in two, and it slips in this direction, that would be considered to be positive shear. And so if I were standing on this section here, looking down at this face once it's been sawed in half, I'm going to be seeing a shear vector pointing vertically. And it's going to be equal to that vertical load over here, because sum of forces in the y direction for this little sawed off segment has got to be 0. So if I got a minus 197 there, I'm going to have plus 197 here. So that's what I started out drawing, and that holds up all the way back to where that support was. Then at that support, I take that support load off of there, and I'm ending up with a negative shear all the way back to the next bearing. Once I've got that, I can simply integrate the area under the shear to get the bending moment. So that bending moment gets greater and greater in the negative direction all the way up to here. Then it starts decreasing back to 0. So hopefully that's fairly old information for you there. Negative shear would be considered something like this, where you have a downward uh, shear vector. Positive bending moment would be where you can catch rainwater in it when it bends. And then the negative would be the opposite of that. Excuse me, let me get a drink of water here. All right. So next topic here I've put in is just a little bit of a review on strain gauges. Been talking about designing certain stress levels or strain levels in parts, and so it comes down to how's an engineer going to determine what that stress is in an actual part. If you had a load on a part and you wanted to actually measure it rather than calculate it, we typically would use strain gauges. That would be into the area of what we would call experimental stress analysis. And so you want to be a bit familiar with strain gauges. Strain gauges are just little grid type resistors that can be applied to a surface with a special adhesive, and then when the surface of the material undergoes strain, the strain gauge itself undergoes strain and changes resistance very minutely. So since it's such a small amount that we're usually dealing with, we typically wire them up in a what's called a Wheatstone bridge, so that we have uh, uh, compression and tension in opposite legs of the Wheatstone bridge, or we can have dummy resistors if we only have one or two arms of the Wheatstone bridge as active strain gauges. And so this problem is saying that we're given a full bridge hookup. That means we have four arms of the bridge active. We're told we have a gauge factor of 2.08. That's information that would be given on the manufacturer's information for the strain gauge you might select. And we're told that we have excitation, or we have excitation voltage of 2.5 across the bridge. And so what we're looking for is we're being told that the load causes the bridge output to be the imbalance in the bridge once we put a load on it is 120 microvolts. And we want to know what is the load in pounds force on this particular shank implement. That's 1 foot from the strain gauge we're applying a load. We have strain gauges on the front side, front gauges in the back. This thing would be in bending. So if we go synthesize our solution, we need to know that for a full bridge circuit, the output voltage over the excitation voltage is going to be the gauge factor times the actual strain in the part, or that actual strain that the strain gauge sees. And so again, following through our basic equations here for bending moment, we can we can come up with 12 inches. That force was applied 12 inches down from the strain gauge, so the bending moment is 12F. Distance from the neutral axis, so that beam to the outer fiber there is 1.5 inches. I think that shank was 3 inches uh, uh, deep. We can calculate our area moment of inertia, and we can calculate our strain here based on our voltage to be 23.1 microstrain. That would be 23.1 times 10 to the minus 6 inches per inch here. And if we plug that into our equation above here, we get that that force was 43.27 pounds of force. So I think let me go back here. Okay, here's if it were a half bridge, what would the force have been? Well, if we had that same voltage out, we just have to know that in the case of a half bridge, we've got dummy resistors and we've got only two active. And if we had the same output voltage, we'd end up basically saying that our force is twice what it was if we had been using a full bridge. So take a look at this. I mean, review this. This is National Instruments, the makers of LabVIEW. It's an excellent little article on strain gauge basics. Might be of benefit to you to be somewhat familiar with that topic out there. In fact, that was a review problem on the P exam previously. Hey, what I think this buckling, column buckling, I've got a section here on column buckling. Let me go through this pretty quickly. I don't think I'm going to go into, you can read this as far as the details of this, but what I mainly want to point out to you as far as column buckling, it's where you'd have a load on a part that would be essentially a column load or an axial load, and the part wouldn't be, it might fail by buckling instead of failing by reaching a yield stress in compression. And if it were a slender part, and if it were long, that would be much more likely than if it were a big fat column. And so what we get into when we're dealing with column buckling, if you started to review that area, here I've given an example of a hydraulic cylinder where we're asked to deal with the size of the rod that we might want to use to prevent column buckling. And ordinarily, in a case like this, if the thing is at full extension and you got some major load on that it's pushing on, you run the risk of having buckling failure in the rod itself. Probably would not have buckling back in the cylinder itself, but in the rod, it's much more slender and lengthy. And so we run into what's called the slenderness ratio, which is the area moment of inertia divided by the cross-sectional area, and you take the square root of that to get what's called the slenderness ratio. And how's that used? Well, let me just advance on here for just a second. It comes down to consideration of end conditions. It makes a lot of difference on how a column responds in column loading. You could have one end cantilevered and one end free. That'd be called free fixed. And we have a factor we call C, 1/4 in that case. Or if it's pinned, then we'd have C of 1. Or pinned, fixed, it might be pinned on one end, guided, but fixed on the other. Then we've got a better situation as far as the column is concerned. So that factor then goes up to 2 if it's fixed. Then a column, a C factor 4. But this critical load factor that we calculate here, 2C, where C is this guy, times pi square E, modulus elasticity for the material, and the divided by SY, yield of the material, square root of that. If the slenderness ratio, L over the slenderness ratio, turns out to be greater than this number, then we're going to have to use an equation called the Euler equation. If it's less than that, then we have a stouter beam. We can design to higher loads. That's what's typically called the J.B. Johnson equation. And so to summarize all of that, if we're trying to get to a critical load divided by the cross-sectional area, and so that's going to equal this amount, where L over the slenderness ratio is greater than this amount. Or we would design our critical load over the cross-sectional area by the J.B. Johnson criteria, which is this, or slenderness ratios that are less than that critical value. So that's sort of it in a nutshell. If you have these equations handy and you're dealing with a column buckling load, I think from the example I've given you there with the cylinder, hopefully you'll be able to figure out how to apply those. And giving you a little more explanation here, walked you through the cylinder design, which I don't think we need to take time for here. The other thing on cylinders, though, I noticed that the current review document on machines has quite a bit on hydraulics. And in this case, you want to be a bit familiar, and I'm assuming most of you are familiar with the hydraulic cylinder, but you've got a piston and the rod. You've got a cross-sectional area on the push side of the piston, which is greater than the cross-sectional area on the retraction side. Excuse me, because over here, the effective area of the cylinder would have to subtract out the cross-sectional area of the rod itself. So you're only dealing with that annulus there for cross-sectional area. So forces involved would be cross-sectional area times pressure. And over here, the retraction force capability would be that annulus cross-sectional area times whatever pressure there is in the rod end of the cylinder. And so that's, you just want, if you're asked to calculate push or retraction force capability, you just want to have an understanding of what you're looking at with a cylinder like this. You can have cylinders that have double-ended cylinders where the rod goes out both ends, and then of course you'd have the same area on both sides of the piston, and that would not be an issue then as far as the differential. here, all I've done here is apply that column buckling um, equations to a little different type of a problem, not a cylinder, but in this case it would be a called a slider crank mechanism. We've got a crank rotating, and we'd have a connector here between it and a reciprocating body or mass, sickle bar, what have you. And so you have compressive and tensile loads appearing in this connector as the rotation takes place. It's changing direction. And so all I've done is, again, gone through thinking through which direction is this thing going to buckle in. If it buckles, your area moment of inertia would be far greater in this direction. So it'd be about IZZ in this case. The thing is likely to buckle about IYY if it were going to buckle. And so just walk through this thing of calculating what that load what would be the critical load for that, where I'm calculating that slenderness ratio, and ended up saying to use the Euler because the L over the slenderness ratio turned out to be greater than that 93.3 in this case. It's 166 actually, which took us to the Euler, not the J.B. Johnson. And then I calculated the allowable load then of 474 pounds. So, as a designer, you can decide what safety factor you might want to use in a case like this. I said here that for safety factor, if we had a critical load of 998 pounds, we had a safety factor of 2, we'd want to be designing for a allowable load of 474, or round it to 500. And so in our actual case, our actual safety factor then would turn out to be 948 over 500 would be 1.8, and we've sacrificed, if we allowed 500, we've sacrificed a little bit of our safety factor there. We're not quite at 2, but that's a designer decision based on economics and a number of other factors. So here I just do a little more with the slenderness ratio. I think you can follow through this if you simply read it. I don't think I'm going to deal with this. This is getting into critical speed of shafts, and basically what it comes down to is at what speed, what rotational speed of a body like this would cause it to hit resonance. That is where it would be undergoing you'd have a speed which is at the resonant frequency of the shaft, which is not a good thing. That would be another definition of failure in the case of design of a shaft, because it would be an unsatisfactory. You have a lot of vibration, a lot of noise, and so on. So there is a method of calculating that. It just comes down to the what's called a Rayleigh-Ritz formula. I wouldn't spend a lot of time on this particular topic probably, but it wouldn't hurt to be a little bit familiar with it perhaps, or have this example with you in case you hit something like this. But basically what this is doing is summing up the weights and the deflections along the length of the shaft, and and then calculating the actual uh, resonant frequency. So basically what it comes down to is what is the deflection in the shaft, and you'd be taking those deflections at various points along the shaft and summing them up to get an approximation. Here, in this case, I just quickly wanted to calculate the deflection in the shaft, and calculated that to be 0.00896 at the midpoint of the shaft, and applied this equation for resonant frequency. Square root of G over the static deflection. G being 386 inches per second square divided by the static deflection in inches gave me 656 radians per second. Converted that to RPM. 6,270 RPM, but the approximate resonant speed for that shaft that you'd want to avoid. You wouldn't want to have to design a shaft where you got to go through that critical speed to get up to operating speed either, and most likely unless it went through it very quickly. So anyway, that sort of wraps up most of what I've got. What I've included here for you is some appendices that has some this reference materials that I've pulled out of various books on machine design that you would want to be maybe at least know where to go to find them. The horsepower equation I gave you earlier was Tn over 63,025, but that was where you were using inch pounds and RPM. Here, this one, 5250, is what you get if you're using torque in pounds, foot-pounds of torque rather than inch pounds. And you can go back to the basic definition of horsepower and force times velocity and divided by 33,000, which would give you horsepower, where velocity is feet per minute in that case, and so on. I would just commend these to you. Some of the stuff here I've already talked about, and some basic data, conversion factors, and you want to have some of this handy for you on your exam in case you need to know how to convert between units. This is one thing here that I usually have to wrestle with my students a little bit to get them to recognize the difference between mass and weight. And so here I've simply run through some basic definitions. 1 Newton is 1 kilogram times 1 meter per second square. 1 pound force is 1 pound mass times acceleration of gravity. So basically what would come out of this if you had an equation where you were dealing with pounds mass, for example, a second order differential equation for vibration, where you had mass times acceleration, but you wanted all your units throughout the thing to come out in terms of pounds force. You would then have to be, instead of having a 1 pound mass, you'd be putting in 1 over 386 pounds force second square per inch in that case. Or the other way to think about it is that at standard gravity, at sea level, 1 pound mass weighs 1 pound force. And not 32 pounds, as some try to do. You got to be sure you're carrying these units along in order to be correct. We would not say that 1 pound mass equals 1 pound force, but it's 1 over 386 pounds force second square per inch. So anyway, that's just for your edification there. And of course, 1 Newton, we would recall, is 2.2 kilograms divided by G, which gives us 22 pounds force, which says that 1 pound force is 4.46 newtons, basically. All right. Well, I think with that, I'll leave it with you, and I want to wish you well on your exam. I hope that this has been of um, some a little bit of help to you. And so, any comments, any questions that anyone might have? All right. Good night.